Cool, thanks. Hey everybody, I'm Paul. Let's talk a little bit about running serverless workloads. So I work for IBM. I work in our open technology division where we work in open source. I specialize in kind of two areas. One is serverless, so things like Knative, Kubernetes, things like that, different container technologies. And then the other area I specialize in is quantum. So we do a lot of work in open quantum around things like post-quantum cryptography, the Qiskit software development kit, and quantum middleware, which is what I'll be speaking a little bit about today. My co-presenter, Dr. Max, couldn't be here. He's on the board of the OpenJS Foundation, and they're having governance meetings this week, so he couldn't make it, unfortunately. But I'll carry the torch. All right. So what are we going to talk about today? Essentially, I want to kind of use this as a chance to do a bit of a case study of running serverless applications and different ways to do so. So one of the things that we had to do on my team is build an application that we're calling Quantum Serverless. So I'm going to use that as kind of our case study to walk through the pros and cons of different serverless techniques today. So the first thing we'll do is we'll talk about kind of what that quantum serverless problem is, what's the thing we're trying to build. Then we'll look at kind of two different ways of building it, one using Knative, one using Ray. And then at the end, we'll look at some lessons learned and some things for further discussion. All right. So the quantum serverless problem. I guess one of the first things to kind of start with is, what's the big deal about quantum computing? Like, why do we care about that? And the short answer is that it enables us to solve some hard problems that we aren't able to solve today. If any of you remember back to algorithms class, there's these things we call NP hard problems that we can't solve. They're non-polynomial time. So they're really, really hard problems. They take exponential amount of time to solve. And what quantum computing does is it enables us to solve some of those hard problems. So things like the traveling salesperson, for example, factoring large numbers. Those are things that with quantum computers we can build efficient solutions to, things that don't run in exponential time but can run in polynomial time. And the key piece of this is to note is that it's not that quantum computers are going to replace classical computers. We aren't going to have quantum computers in our pockets or in our laptops, at least not any time in the foreseeable future. But it's classical in combination with quantum that is where we get these speed ups. And what do I mean by that? Sorry, these slides are a slight bit out of order. All right, bear with me 1 second. Sorry. All right, sorry about that. Okay, where were we? Classical and quantum combined. And to think about kind of what this would look like is that when we're building any type of application, it's not just a single thing that we're trying to solve. There are multiple pieces that we want to do in any particular application. It breaks down into a set of different sub-problems. And essentially what we want to do is we want to optimize each particular sub-problem so that it runs in the type of environment that provides the optimal solution for it. So it might be that, sub-problem 1 runs best in classical compute. So we'll run it in classical compute. It might be that sub-problem 2 runs better as a quantum algorithm. So we'll run it in quantum. But the key is that we want to optimize those individual pieces so they run in the best place possible. And kind of the marrying of these classical and quantum compute as we orchestrate these workloads is kind of what we're calling middleware for quantum serverless. Again, the combination of classical and quantum. And the point being that when a user has an application, they write it up, they send it out, and middleware can essentially farm it out to the right place for it to run, whether it's quantum, whether it's classical, whether it's HPC, whatever it happens to be. So that's abstract. Let's look at this a bit more specifically. Let's look at an example of something we call circuit knitting. So we have a quantum circuit here on the left, and we're going to talk a little high level here, but we got a quantum circuit on the left. And essentially what circuit knitting is the ability to cut a circuit into two smaller circuits that are mathematically equivalent to the larger circuit. So this has applications in a number of places. One, if you were trying to run a big circuit on a small machine, You can cut it into smaller circuits that can fit into that machine. The other is that the two smaller circuits might run faster than the one larger circuit. So what would this workload look like? This would be, this is just, again, kind of a high level, kind of what this might look like. But when we write their program to do some circuit knitting, you would send your program out to the cloud. You would run a cloud step that would decompose, do that circuit cutting aspect, where you would cut it into two smaller circuits. You would then farm the quantum circuits out to quantum computers in parallel. Those results would run. You would pull them back to classical, reconstruct the results, build it, and send it back to your program. And that's quantum middleware in a very, very high-level overview. So how do we build that? And essentially, there are two choices that seemed that we looked at. We looked at Knative, which is what my team's very familiar with. We also looked at Ray. So how do we compare these two? The easiest thing to do was basically build the two and see what happens. So that's what we're going to do now, is look at how we built each of these applications. All right. So just a little bit of background. Quantum programs are usually written in Python using kind of the Qiskit SDK. And this is a very, very high-level example of what something like that might look like. It's Python, so it's nice and simple. We're doing some pre-processing where we're building in lines like 6 through 11 where we're building the circuit. Then in like 13 and 15 is where we're running the circuit. And then 17 and 18 are kind of pulling the results back from the run circuit. So classical, quantum, classical. Okay. So essentially our problem is we have to figure out how do we run this application. So if we're going to use Knative, let's talk a little bit about what Knative is. Knative is really a way to simplify running applications on Kubernetes. And it's composed of three core parts and some other parts, but each of those parts can be used independently or together. And they each aim to kind of simplify a certain piece of the work in Kubernetes. So functions are a very easy way to kind of replicate the Lambda functionality in Kubernetes. It's you have some code, and I want to run it. I don't care how it runs, just run it for me. You can use functions to take that code and turn it into a runnable container with just one line. So you don't have to worry about any of the build, any of the packaging, anything like that. Functions take care of that for you. Eventing, if you have event-driven workflows, eventing gives you a single interface for a variety of sources and sinks, so you can chain those events together using a single API in a declarative fashion. And then serving, if you have a container that speaks HTTP, serving will allow you to take that container and run it and do all the background pieces that you might not want to have to worry about. Things like scaling requests, managing rollbacks and revisions, or the updates you make to your application, health checks, and all the security pieces that you would want to do. All right. Again, high-level Knative. So what might this look like? If we're going to run this as a demo on Knative, and bear with me as I switch the displays around here. All right. So on the left, can we read this at all? All right. See if I can make it a little bigger too. Essentially what we have running, we've got a Knative service. It's got that URL point. Basically what we're going to do is we're going to take our application, we're going to package that code, ship it off to Knative, let Knative run it, and spit results back to us. Now you'll notice in the second line there, we don't have any pods up here currently. Knative scales down to 0 when it's not running. So when we go through, and bear with me one second, and we run this, which is this code right here, it's just going to run this. We define a function, we give it a decorator, like we're familiar with, to run it remotely. We run it and pull back results. What we're going to see happen is, and I should have been watching, you'll see a new pod that spins up to handle that request. So if we watch these logs and we want to run a bunch of these, for example, we can run 10 of these. We'll see kind of 10 new results pop up. And that's Knative running quantum service. We have some code we want to run. We send it out. We let Knative run it. Spits it back. It's nice. Where were we? So we ran our demo. Okay, now there's a couple of pain points in running this in Knative. One is that everything's built, Knative uses containers. So containers can sometimes take a while to build. They can sometimes take a while to start. So kind of the startup time can be problematic in Knative. But the second piece that's really problematic is if we want to, that was a very simple example. We ran one circuit and returned a result. But if I want to run multiple workloads or multiple steps of a workflow, we can't really manage that in Knative. We need something else over top of it to do that. So that kind of becomes a really big pain point because a lot of our workloads are not just run it once and forget about it. They're iterative processes. That sounds familiar. That sounds like something Ray does fairly well. I'm not going to spend a lot of time talking about Ray since it's Ray Summit. I assume we're all familiar with it. But we can chain these workloads together really, really well. We can run them in Kubernetes using kuberay. And in fact, the workflow I showed before, very, very simple to do that in Ray. It's just you use the Ray decorator to run remote. You can run your jobs remotely. It pulls it back. So essentially, we had reinvented that in Knative. Now, with kind of the standard Ray distributed task, we did run into a couple of pain points. One's the issue of ephemeral compute. We don't want to leave things running when we don't need them. And I think the Ray Jobs API is still in alpha at this point, or at least it was when the last time I checked. So not quite ready for production yet. So we had to kind of come up with a solution for ourselves there. And the other piece, kind of if multi-tenancy, if we, running one person in a cluster is great, but if we want to run multiple people, how do we manage those resources? How do we keep those secure? How do we keep those isolated? And so we did a little bit of tweaking around to get there. So let's see what this might look like in Ray. All right. All right, so I just switched to a different cluster that has Ray running on it. So you can see we've got some pods up here that are running. We'll make that a little bigger so we can read that. So we've got a gateway that handles the requests. I've got a Jupyter notebook running, which is where I'm going to run this thing, some background stuff to manage state, and a scheduler, which is what handles running the applications. So I'm going to just also throw the scheduler logs over here so we can kind of watch this go. Let's make that a little bigger too. Okay, and now to run a program, essentially what we did to run a program, again, can we read, this is code that we're gonna run. Instead of running it in a Jupyter notebook, we've got it saved as a file. We're gonna run that file, so we'll ship that whole file off to Ray to let it run for us. So we'll do some fun things like this. We'll import it. We've got a provider, which is just kind of our wrapper that handles the scheduling for us. And then let's run our program. What we'll see happen here in the top is all of a sudden we're going to spin up, there we go. At the very top, we spun up a Ray head node and a Ray worker node for this specific application mapped to this username. So you see user, whatever that hash is, that's who I am right now. It's always fun doing these things live on hotel Wi-Fi because you never know if it's going to work or not. It worked earlier, so we'll keep our fingers crossed. But we're going to see the pod is going to, but once the head and the worker are running, we'll see down here that the head node, you see in the logs, it's not ready yet. If we wanted to, we can take a look and check the job status, and it'll show it's queued. Okay, now we're both running. We're going to connect. The job's been accepted. I guess I could look down here and see, or here and see what it's saying too. Did it succeed? Did I miss it succeeding? I did miss it succeeding. The job succeeded. And then what you're going to see happen is the head and the worker nodes will terminate and they'll spin down. And any user that's logged in can, will spin up their own things in their own kind of isolated pods. Nice and fun. All right. Okay. Lessons learned. This went a lot quicker than I thought. Lessons learned. So I guess one of the first things that kind of we learned in doing this exercise is that Knative and Ray, we're talking about running serverless applications. They operate in slightly different spaces. There's a lot of overlap, but there's some differences amongst them as well. Both allow you to run distributed applications. You can use Ray Core to do that. If you're using Ray, you can use functions to do that in Knative. You can run in Kubernetes, Ray cluster versus the Knative K service lets you run in Kubernetes. And serving, both the applications that are called serve or serving handle that. Because of Ray's focus on kind of ML, AI, and that type of workspace, the train, the tune, the data, those applications, there's not an equivalent in Knative. So that's kind of a space where Knative doesn't, so particularly when you're doing kind of iterative data type workloads, it's not a place where Knative works very strongly. At the same time, Knative has eventing, Ray doesn't. So again, it's just kind of outlined that there are some differences between the two different types of applications. All right, so lessons learned, or kind of more broadly speaking, some things for further reflection. I think the biggest thing that we learned, that kind of missing parallelism in Knative was really made it hard to do the type of work that we wanted to do in Knative. Because you're looking at a container, which is kind of its own isolated thing, if you want to send work out and back, it requires writing something on top of it. So the container is not necessarily the ideal structure for running these types of workloads. Again, a lot of the differences between Knative and Ray comes down to the question of what are we talking about? What's the object we're working with? Ray works with distributed objects, code that we're sending around to run in multiple different places, whereas Knative's working with containers, isolated, autonomous, stateless entities. Again, Knative is, this is in the name, Kubernetes native. So Knative runs kind of as a first level artifact in Kubernetes. Ray, you kind of have to pile a little bit abstractions on top of to run in Kubernetes. Is that an issue? Depends on your workload. But Knative is a little closer to the ground. The question becomes, is that important? Do we always want to run things in Kubernetes? Is it better to run some things in HPCs, some things on bare metal? Is cloud always the right question? Again, I think for some AI workloads, the closer you can get down to the hardware, perhaps the better off you are. And then lastly, kind of one thing just worth mentioning is that, for open source projects, foundations do matter. Knative is in the CNCF. It wasn't initially, which caused a bit of a kerfluffle, for lack of a better term. But, foundations provide, vendor-neutral governance standards. The things won't, licenses won't change on you out from underneath you, things along those lines. So the importance of a foundation for a good open source project is key. So, wow. All right. So that's pretty much all I had. This went a lot quicker than I thought it would. I'll leave these up here. If you want to learn more about quantum computing or Qiskit or quantum serverless, you can snap some pictures. These links are also in the slides. Otherwise, I guess we got time for questions. No? Sure.
So, thank you. Just referring to what you said about containers versus objects. So one advantage of containers is that you can put all your dependencies there and have another container with completely different environment running, in the same app. And I just wonder if you encountered that issue in Ray and how did you deal with it? Like managing, dependencies of your workloads.
Yeah, so that's been a not fun problem. So we've essentially had to package up, when someone, bear with me 1 second, I'll see if I can pull this back up. When we were writing programs, there's a way to pass in dependencies, which is basically Python modules. But yeah, we basically have to kind of tar up all the dependencies that someone wants to use, any packages someone wants to use, and ship them along with it, which is, not pleasant. Is it less pleasant than having to write a distributed scheduler? So far, yes. So it's just kind of why we went that way. But you're right, the containers definitely allow you to kind of get out of that dependency management piece of it. So yeah, that's a good point, yes. Yeah, there was, I think, someone.
Thank you. Yeah, so I know Knative has the Kubernetes pod autoscaler, and it also has support for the HPA, horizontal pod autoscaler. Mm-hmm. Ray has Ray autoscaler. So how do you reconcile? Which one do you use? What do you recommend?
So It depends on what you're trying to scale. So Knative scales based on basically number of requests that are in flight. So if you're, which is particularly good if you're running like an HTTP service where I've got, I'm processing requests as they come in. And the Knative autoscaler is really based on like, if you start to get a backlog of requests coming in, let's spin up more instances so that we have, enough to handle all the requests that are coming in. The Kubernetes autoscaler is based more on like the compute level. So like, are you topped out on resource usage and spin up that way? They're really just, it depends on the application in terms of which one makes the most sense, how you want to, which metric are you tracking, which is the thing that matters. Is it number of requests, is it resource usage? So it kind of depends on the application you're running in terms of which one makes the most sense.
Cool. If there are no other questions, I also have a question.
Okay.
So I'm curious about sort of, you said you're stitching together quantum resources and I guess typically programs that don't really need quantum resources.
Mm-hmm.
And I'm wondering what the criteria are for that. So I would kind of expect like a pure deterministic function doesn't need to use quantum resources, but is there something else that like, are you measuring based on runtime, like total resource usage? How do you determine?
Yeah, so it's going to be application specific, but it's going to depend on, the real question is there a quantum algorithm that runs faster than the classical one? The canonical example of this is factoring like large numbers into 2 prime numbers. The classical algorithm's exponential. It takes forever and a day to get an answer. But if you use like Peter Shor's algorithm, which was able to reduce that by, not to get too much into the math, but it was basically able to, you find patterns and you can basically kind of do those overlays and you can chop out parts of the application so you can run it, you remove steps basically to run it. So it runs essentially in, I think it's like basically like almost linear time. So the key question is there a quantum algorithm you can use? So the way quantum works is you have what they call qubits, which are zeros, or it's an electron with a spin on it that you use to represent 0 or 1. But unlike a regular bit, it's not just 0 or 1. It can be any and all possible combinations of 0 and 1. So you exponentially increase the amount of states or the states you can represent at the outset. So if you can use that efficiently, you can process so many more results at once because you're doing 30 or so at once instead of just 1 at once.
I see. So the users determine what resources they expect. Like you're not automatically routing.
No, not at this point. No. I mean, long term that would be nice, but right now it's really like, is there a quantum algorithm you can use? So yes, I want to run this as quantum. So am I going to run like a quantum Monte Carlo simulation? Am I going to run a quantum representation of chemistry molecules?
That makes sense. Thanks.
Cool. Yeah.
So when we talk about serverless or functional as a service, so I think the function start time matters, right? Do we measure some performance between Ray and Knative?
I can't hear you.
Can you hear me now?
Yeah.
Okay. So when we talk about serverless or functional as a service, and I think the function start matter. And do we measure the performance in terms of the latency of the function stop times between Knative and Ray? And what's the pain point you are seeing right now?
Yeah, so I didn't do a measurement. I know Knative roughly can take up to 2 seconds to start from a cold start. I didn't measure Ray off the top of my head, but it seemed to be a little quicker. Again, there's obviously like network latencies and things can matter in there. Mm-hmm. But I didn't do a direct one-to-one comparison in terms of trying to measure.
How about throughput?
Sorry?
Throughput, like for example, in a single, like say, 1 second, how many functions you want to launch in your application?
Yeah, I didn't do any benchmarking of the two. Yeah. The only piece I know is that Knative can take a long time, but I didn't do a direct benchmark. Basically, when we got to the point where we could run one task, but if we wanted to run multiple, it was kind of like, well, Knative is not really the way to go on this, so we kind of left it aside.
Got it. Thank you.
Yep.